Hi everyone, it's Michael. So I have another very nice problem for you guys today. This one I found on the Art of Problem Solving forum, but the poster did not give a source. So I would be very interested in where it came from, so if anyone knows, please let me know. And if you want to try to solve it, feel free to pause the video. Alright, so now I'm going to go over it. In triangle ABC, we have an inscribed circle, omega, and it's tangent to the sides BC, AC, and AB at PK and N. BK intersects the circle at point L. T is the intersection of AL and KN, and Q is the intersection of CL and KP. And we want to show that BK, NQ, and PT are concurrent. So I feel like these concurrency problems are often, I find them pretty tricky, and I only know of really two good ways to start in most situations. So either using Cheva's theorem, which is what I'm going to do here, or what you can do is, for example, if I showed that PT cuts the line BK in the same ratio that QN cuts it, then that would also show they're concurrent. But this time I'm going to go with Cheva's theorem. Now, if someone has a purely synthetic way of showing this without needing any algebra or ratios, I'd love to see it. Because I'd really like to try to see if there's a way to solve these concurrency problems that doesn't use so much algebra. But that is the approach that I ended up doing, and so that's what I'm going to show you here. Okay, so I want to use Cheva's theorem to show that BK, NQ, and PT are concurrent. So what triangle would I want to use? Well, I'm going to want to use triangle NKP, and so eventually I'm going to want to label this point, I'm going to label it D eventually. So if I want to show that NQ, PT, and BK are concurrent, that's the same as, well, BK would be the same as DK if D were the intersection point here. So I want to show that NT over TK times KQ over QP times PD over DN is 1. So in that case, I would need the ratios NT over TK and PQ over QK. So I can get a handle on those ratios using Menelaus. So that's what I'm going to start by doing. So if I want to find NT over TK, I can apply Menelaus' theorem to the triangle ABL. And so that's what I'm going to do right here. Actually, first I'm going to find PQ over QK. So for those of you that know Menelaus, we have CP over PB times BL over LK times KQ over QP equals 1. If you don't know Menelaus, I would recommend Googling it or looking it up on Wikipedia, and I might do a video on it later. But it's a very useful theorem that comes in handy a lot. And often problems that involve Menelaus, often there's another way to do it just using cross ratios or projective geometry. So if anyone knows of a way to get around using Menelaus, feel free to let me know in the comments. Then we can similarly use Menelaus to find TK over KN. So we have AN over AB times BL over LK times KT over TN equals 1. Okay, so these two equations give us the ratio KP over QP and KT over TN. Now we want to let, like I said, we want to label the intersection D of PN and BK, and we want to see if we can get ND over DP, if we can get that in an equation. So my approach here is going to try to be to use cross ratios. So if you look at the points ND and P and you project them through B onto the line AC, they map onto AK and C. But to use cross ratios, we need 4 points instead of 3. So what is the other point that I'm going to use on this line? So I'm going to take the angle bisector of angle B, and I'm going to let it intersect side AC at E and NP at F. And these are convenient points because E would be where the angle bisector meets AC, so we could use the angle bisector theorem. And F is where the angle bisector meets NP, and it's easy to see that that has to be the midpoint of NP. So now we can use cross ratios pretty efficiently. So yeah, so NF has to equal FP by symmetry because BN and BP are both tangents to the circle. So it's pretty clear that the line BI being an angle bisector has to cut the segment PN in half. Okay. And then, like I mentioned, we can use the angle bisector theorem on point E, which is pretty convenient. So since BE is an angle bisector, we have AB over AE is CB over CE. Okay. And now we are ready to apply the cross ratios. So the cross ratio of the points NP and DF, well, N corresponds to point A. So we're taking a projection through B through these 4 points and onto line AC. So N goes to point A, P goes to point C, obviously, D goes to point K, and F goes to point E. So the two cross ratios here have to be equal, and by the very definition of the cross ratio, so I've shown the definition of the cross ratio in one of my earlier videos. I can't remember exactly which one, but if you're curious, I can let you know in the comments. But by the very definition of cross ratio, so this cross ratio would be, so it's what ratio does D divide NP into? So that would be ND over DP, and then divided by the ratio that F divides it into, which is NF over FP. So if you work it out and do the same thing with both these cross ratios, you get this is ND over DP times PF over FN, and this one is AK over CK times CE over AE. Okay, and a lot of things here would simplify because we know that NF is FP, so this fraction here is just 1, and by the angle bisector theorem, AE over CE from this equation is AB over BC. So I'm not even going to do all the cancellation now. I'm just going to leave all the algebra to one step at the end. But we have this equation, the two equations from Menelaus. Now, the two equations from Menelaus, for example, this one involves AN, but this involves AK instead. And so it turns out AK is equal to AN because they're both tangents to the incircle. And so if we want all the algebra to cancel, we're going to want to use that fact. So we have AK is equal to AN, and by the same logic, CK is equal to CP because they're both tangents. And we want to use that fact because when we do all the algebra, we want this CK to cancel with this CP. And now we really have all the algebra. We have all the equations that we need for everything to cancel nicely for Cheva's theorem to work. Okay, so I'm not going to write out all the algebra, but if you combine all these equations, you get exactly what you need for Cheva's theorem on triangle KNP. So combining all these equations, you get KT over TN times ND over DP times PQ over QK is equal to 1. And that's why I did all this in the first place, was because I was trying to get this equation. And once we have this equation by the converse of Cheva's theorem, we know that dk, nq, and pt are concurrent, and dk is the same as bk, so therefore we know that bk, nq, and pt are concurrent. So that solves the problem. And if you guys know of any other way to solve it. And if you can think of something where I can actually avoid ratios, I'd love to see it. Because concurrency problems, I'd like to see if there's a way where you can like avoid algebra in general. But yeah, just a few months ago, I was afraid of using cross ratios like this, but now I love doing it. It's super handy. So if you like this video, give it a thumbs up. And if you want to see more like this, subscribe to my channel. Thanks, everyone.